Get started. Yeah. So in yesterday's class, 1 minute. Those who are online, are you able to hear me?
Yes, sir.
Okay. So listen. So yesterday we saw what is Gauss law, right? What did it say? This the loop integral or the surface integral of E vector dot dA vector is equal to 1 by epsilon naught times charge enclosed by the Gaussian surface, right? So having that concept in mind, we are going to apply, we are going to see how to apply this Gauss law to derive the electric field due to different kinds of systems. So let's get started with it. Okay. So for that, write down the note. So steps to apply Gauss law. First, consider the type of charge distribution and define the type of charge density. So consider the type of charge distribution and define the type of charge density. That is the first step. Second is consider the point and distance from the charge distribution. Consider the point and distance from the charge distribution. Third, okay, consider the Gaussian surface passing, 1 minute, consider the Gaussian surface symmetric to the charge distribution and ensure it passes through the point where field is to be calculated. Consider the Gaussian surface symmetric to the charge distribution and ensure it passes through the point where the field is to be calculated. Okay. Consider a small element dA on the Gaussian surface. Consider a small element dA on the Gaussian surface and assign direction to it. Fifth, find the direction of electric field from the charge distribution. Find the direction of electric field from the charge distribution. 6. Apply E vector dot dA vector is equal to, or apply loop integral of E vector dot dA vector is equal to 1 by epsilon naught times the charge enclosed. Seventh is solve for E. So that will give you the answer. Solve for E. Okay, having all these points in mind. Okay. So having all these points in mind, we will derive the electric field due to a linear charge distribution, right, using Gauss law. But before that, I need to tell you about the charge distribution. So under charge distribution, you have three concepts. One is called as linear charge distribution. Second, you have surface charge distribution, and you have volume charge distribution. So you have linear charge distribution, surface charge distribution, and volume charge distribution. I'll tell you what it is. So if at all you have an extended linear surface on which charge is distributed. Okay. And let's say the linear surface is of length L, and the total charge here is capital Q. Then you define a parameter lambda, which is called as linear charge density, which is given as Q divided by L. So what is this? This is called as linear charge what? Density. Are you able to understand what I'm trying to say? So this term you would have seen, right? Linear mass density in your 11th standard. In a similar way, you have something called as linear charge density, in the sense charge distributed over the length. Second, what do you have? You have an aerial vector. Yeah.
Can you please scroll up a bit?
Sure. Is this enough?
Yes, sir. Thank you, sir.
So let me know if you're done.
Yes, sir. You can continue.
Yeah. So listen. So if the charge is distributed over an area, okay, if the charge is distributed over an area, then you define a parameter called sigma, which is Q divided by A. What does the sigma stand for? It is the surface charge density. Third, when you have a volume present and the charge is distributed over the volume, okay, if it is distributed over a volume, then you define a parameter rho, which is called as Q divided by V. And what is this called as? This is called as volume charge density. Is that clear? Volume charge density. Right. So if you're clear with all these concepts, we'll proceed with the derivation. Any doubt in this? Clear, no? Okay. So shall we start applying Gauss law? So listen. you have a linear charge that is given here. You're able to see, no? You have a linear charge that is given here, and your job is to find the electric field due to the system at a point P, which is at a distance r from the charge distribution. Here, so what are the steps? First, consider the type of charge distribution and define the type of charge density. So what is the type of charge density you can define? So name is derive an expression for a field due to an infinitely long straight charged wire. So there is a wire which is charged and it is linear in nature. Then what are we supposed to do here? What do we do first? Lambda is equal to Q divided by L. Okay. Or I will not even write it as Q by L. I will first define the charge density, that is lambda, accepted. Okay. And the second step is you need to consider the point where you're trying to calculate the field. Once you know the point, what are you supposed to do, guys? Once you know this point, what are we supposed to do? You need to consider a point after that. You took the distance also r. Then consider a Gaussian surface. So when you say Gaussian surface, right? Did I say it should be symmetric? Consider a Gaussian surface which is symmetric with respect to charge distribution, and you also need to ensure it passes through the point where you're trying to calculate the field. So for a linear charge distribution, the Gaussian surface that we can think of is a cylinder. Okay, the Gaussian surface that is symmetric with respect to a linear charge distribution is a cylinder. If you consider a cylinder of height L and its radius is still going to be this distance r, accepted, because we have assumed that it is passing through the point where we are trying to calculate the field. Are these three steps clear? So what is the fourth step? Okay, so you will do one thing. Okay, so when I say one step, you draw it in your notes. Don't copy the exact diagram. First, draw the linear charge. Linear charge need not be this fat. You can just draw a line. Just draw a line and put a positive sign on top of it like this. Like this. Okay. Then beside it, in the left, so make sure your diagram is on the right extreme. In the left hand side, type of charge density, you can write it as lambda. So type of charge density is lambda. Am I right? So what is the next step? Consider a point P, right? So from there, consider a point P, which is at a distance r from it. So what is the distance between point and a line? It is always the perpendicular distance. And if you take this, the distance to be r, right? So you're done with the second step. What is the third step? Gaussian surface. So on the left hand side, make a note. A symmetrical surface with respect to linear charge. Symmetrical surface with respect to a linear charge is what? The cylinder. Symmetrical shape with respect to a linear charge distribution is a cylinder. So having said this, draw a cylinder with length L and radius r. Radius r in the sense the cylinder should pass through the point where you're trying to calculate the field. So is it clear? You understood the steps? What is the next step? On the Gaussian surface, consider a small element dA. Is that right? So on the Gaussian surface, I will consider a small element dA. One element will be on the curved surface. There will be other two elements which are present on the flat surfaces. So one ds or dA. Some books use ds. I use dA. That is the only difference. Okay. So ds or dA represents the surface area, the area of that small portion. So this is 1 and this is 2 and this is 3. Okay. Now you need to consider the direction for ds. So what is the direction of ds? I think For the curved surface, it is away. For the flat surfaces, it is above and below. Accepted? What is the next step that I gave you? Find the direction of electric field due to the with the help of charge distribution. So if there is a linear charge that is present, what will be the direction of electric field? It is away from it. So here also it is away, here also it is away. So the direction of electric field is away. So you can draw it like this. Just take one arrow mark. So if that is the direction of electric field, what is the next step? Apply the surface integral of E dot dA is equal to 1 by epsilon naught times Q enclosed, correct? So the surface integral of E is E only into what is ds? It is dA into cos how much? Electric field and areal vector on the curved surface are electric field and areal vector on the curved surface are parallel to each other. Plus the electric field with respect to two other areas on the flat surfaces is perpendicular. So the electric flux through the top surface and the bottom surface is going to be zero. So where is the flux coming out? Only through the curved surface. Is it clear? So the loop integral of E dot dA or E into dA cos phi or cos 0 is equal to 1 divided by epsilon naught times what is charge enclosed. That is what we need to find. So charge enclosed is observed, it is lambda into capital L. Why? So lambda is equal to Q divided by L, no? Upper Q is equal to lambda into L. So if this is the case, I told the last step is solve for E. So what you can do is electric field at a given distance is a constant. So if the electric field comes out of the integral, E into the surface integral of dA is equal to lambda into L divided by epsilon naught, accepted. Right. So first step of mathematical equation, second step of mathematical equation, then E into what is the surface integral of dA? Means if you add all these A's on the curved surface, what area will you get? You will get the curved surface area of the cylinder. But what is curved surface area of cylinder? 2 pi r into L, and right hand side is lambda L divided by epsilon naught. L and L will get cancelled. E will be equal to lambda divided by 2 pi epsilon naught r. Is it clear, guys? So this will be the mathematical expression for electric field due to whom? Electric field due to a linear charge distribution at a distance r from it. I'll tell you. If at all you want to take this as a point, you want to join from here, right? If you 90, this side also, but you are applying. Did you learn this concept anywhere in your competitive exam? That is not applicable here because if you go and revisit the derivation, right, you would have derived it using Coulomb's law. If you want to tell you what they would have done, this is taken as dq, and due to this dq, the electric field will be in this direction dE. Then they would have resolved it into components dE cos theta and then dθ. So then they will integrate it. That you should not do it here because yesterday I told you, right, you're not applying Coulomb's law. What is the name of it? So you need to apply Gauss law to derive the same expression. Maybe if you use Coulomb's law, you will get the same value. What you told is 100% right. But that one, I will explain it in magnetic effects of current. So in this, it's not a part of CBSE, so I'm not teaching. Okay. So is it clear, guys? So lambda divided by 2 pi epsilon naught, R is going to be the answer. So just take a minute, go through the derivation, see if every step is clear. If there is any doubt, ask. Just go through it once. Clear? I'm assuming that every step is clear, right? So next, obviously, once you complete linear, then you need to go for area. But area we'll see it at the end. I'll go to spherical part. But before that, this is the expression which I told you. Lambda is equal to, E is equal to lambda divided by 2 pi epsilon naught r. There is one thing that is not there in your textbook. That is, how will the graph between electric field and the distance be? So if you look at the expression, what do you get in your mind? E is inversely proportional to R. What shape will you get? You will get a shape something like this. Any idea about what is the name of this? It's called a rectangular hyperbola. You would have studied hyperbola, right? So rectangular hyperbola is the one which is tilted in 45 degrees. So to put it in simple terms, if a hyperbola with respect to an axis is like this, if you turn it in this way, in your CBS, you don't have the concept called as asymptotes. So if the x and the y axis acts something called as asymptotes, just have this word in your mind. You need not worry about what it is. If x and y axis acts as an asymptote for a hyperbola, that kind of a hyperbola is called as a rectangular hyperbola. Okay, this rectangular hyperbola you have seen in some other chapter as well in your thermodynamics. Can you tell me where it is? Isothermal process. It's called as an isotherm, right? That is also a rectangular hyperbola. According to mathematics, it is rectangular hyperbola. According to physics, it is isotherm. In a similar way, according to mathematics, it is rectangular hyperbola. According to physics, no name, just a graph. Okay. So I hope I'm clear, right? If at all the linear charge distribution is positive, the electric field is outside. If it is negative, it is inward. That's it, right? So if this is clear, we'll proceed to the next part. So the next part is we need to derive an expression. So here also what you're doing is you're still applying Gauss law. Don't forget it. It is an application of it. Derive an expression for electric field due to an uniformly charged spherical shell. It is not a spherical charge. What is the difference, guys? So what is the difference between a sphere and a spherical shell? So when you
Spherical shell is hollow.
Very good. Yeah. Spherical shell is hollow in the sense, if you try to give charge to a sphere, okay, what will happen is the charge will get distributed throughout the sphere. Then that will become a three-dimensional shape. Whereas in the case of a spherical shell, one important point to be noted, sphere means what comes to our mind? Three-dimensional, right? So you will start defining what kind of charge density, volume charge density, but you're not supposed to do it because when you give charge to that particular material, it can go and sit only in the place where matter is present. So when inside it is going to be hollow, where will the charge go and sit? Only on the surface. So when the charge is sitting on the surface, where is it sitting? Is it sitting inside a volume or is it sitting inside? Is it sitting on a surface area? It is sitting on a surface area. That is why it is very important. This is very common mistake that people do. So when you see spherical shell, what kind of charge density you should define? Surface charge density. Never go for volume charge density. Okay. So we'll follow the steps again. Tell me. So when you talk about a spherical shell, right, we need to calculate the electric field at 3 points. One is inside the shell, second is on the shell, and the third is outside the shell. So we will start with outside the shell. Okay, when I say outside the shell, with respect to the center, I need to consider a point P which is outside. Let me say the distance is R. Okay, so this is point P. So what is the second step? You need to consider type of charge distribution. So what is sigma base? The total charge by area. What is the area of a sphere? 4 pi capital R square. So here capital R is the radius of the spherical shell. Small r is the variable distance from the center to any point. Okay. And this is the case. What is the next step? Consider a Gaussian surface passing through the point where you're trying to calculate the field. And at the same time, it should be symmetric with respect to charge distribution. This is the best symmetry you can ever get. So spherical shell is already a symmetrical shape. What will be the best symmetry with respect to it? Consider another concentric spherical shell or concentric sphere. So that this is what the Gaussian surface is. So as I'm telling, right, you keep drawing one by one, like how you did in the previous case. So first what we will do, draw a spherical shell, that is this one. So draw a spherical shell and consider the charge on top of it. Right? Then take a point P outside the spherical shell. And from the center to that point P, from the center to the point P, consider the distance to be R. Right? Next step. Consider a Gaussian surface, that is another concentric sphere. And it should pass through where? Pass through P. So obviously the radius of that Gaussian surface should be the distance from the center to the point where you're trying to calculate the field. Is there any doubt till this step? So from the surface to point P. No, why I'm taking smaller is later I'll create a relation between smaller and capital R. So generally when you're taking this kind of a scenario, the distance is always measured from where? From the center. Okay. Is that clear? So after that, what are we supposed to do? On the Gaussian surface, consider a small area. So if I consider a small area like this, then the direction of this areal vector is going to be in this way. That is dA. Accepted? I draw this. So small area, its direction is dA. Now, what are we supposed to do? Surface integral of E vector dot dA vector. Okay, or I can write E into dA into cos 0 degrees. Accepted? Because the electric field is radially outward and the areal vector is also radially outward. So the angle between them is 0. So cos 0 degrees is equal to, what should I write on the right hand side? 1 by epsilon naught times the total charge enclosed by the Gaussian surface. So how much charge is the Gaussian surface actually covering? It is covering the total charge. Is it not covering the total charge? So can I call it as capital Q itself? So where capital Q is this total charge. Are you able to understand what I'm trying to say? So these kind of small pieces are there, right? Let's say the small pieces are dq, dq, dq like that. If you add all those dqs, the total charge on the spherical shell will come out as capital Q. Okay, that capital Q is what I've written here. Now, the surface integral of E into dA into cos 0 degrees. So what can come out of the integral? E will come out. E into the surface integral of dA is equal to Q divided by epsilon naught. So if I add all the dAs present on the Gaussian surface, what will I get? That is the area of whom? area of the sphere. But which sphere am I talking about? Is it the source or the Gaussian surface? Look where dA is. Gaussian surface. So when you add all the dAs will be a part of Gaussian surface. They should get added to give you the area of the Gaussian surface. So what is the area of Gaussian surface? 4 pi. This is where you need to be careful. It is small r square. Never make that mistake. Some people write it as capital R square. Don't do that. Is there anyone named Ramamuthu Kumaran? Ramamuthu Kumaran. Okay. Right. So E into 4 pi r square is equal to Q divided by epsilon naught. So E will be equal to capital Q divided by 4 pi epsilon naught small r square. Accepted. So this is going to be the value of electric field outside the spherical shell. At a distance of how much value? At a distance of small r from where? From the center of the spherical shell. So Q divided by 4 pi epsilon naught r square. Is it clear? Now, when this is the spherical shell, at this point you're trying to calculate the field. Then the electric field at this point, if it is equal to Q divided by 4 pi epsilon naught small r square, then on the surface, I can say small r is equal to capital R. Right? On the surface, what will happen? Small r will be equal to capital R. If I take this and substitute it here, what will I get? E will be equal to Q divided by 4 pi epsilon naught capital R square. Okay? Is that clear? On the surface, see this Gaussian surface, and they are the same. So Q divided by 4 pi epsilon naught R square. Niranjan, you asked this yesterday, right? You remember you asked the question, what will happen on the surface? Okay, the charge will participate. Okay. Similarly, if you take the Gaussian surface to be inside, okay, to take it to be inside, then this distance will be small r, this distance will be capital R. Okay. Now comes an important question. The surface integral of E vector dot dA vector is equal to how much? 1 by epsilon naught times the charge enclosed by the Gaussian surface. But in this scenario, what is happening? Is there any charge present inside? No, because all the charge is going and sitting on the surface. Since charge enclosed is equal to 0, this value goes and sits here, then the electric field inside the spherical shell is 0. This is a very, very, very important property of a conductor. Okay. Is there anyone having a doubt? Those who are online, any doubt? Not necessary. Not in this case, it is not necessary. We substituted here. It is not necessary because the values are directly coming out. So there we substituted because it was an infinitely long wire, but the Gaussian surface you considered had a finite length. That is why we tried to write in terms of linear charge density and the length of the Gaussian surface. But here what is happening? The Gaussian surface itself is covering the whole charge. If this is the charge now, you took the Gaussian surface, right? Within this Gaussian surface, this whole sphere is there. So that is why we need not write it in terms of smaller. That is the reason. Am I clear? Right. So what is happening? Electric field, if I write it as a function of R, then I can say that it is equal to Q divided by, okay, I'll write it like this. It is equal to 0 for R less than capital R, accepted. When the value of small r is less than the radius itself, it is this value. Q divided by 4 pi epsilon naught, capital R square, when small r is equal to capital R. And Q divided by 4 pi epsilon naught, small r square, when small r is greater than capital R. Correct? So this is a very, very important expression, and this is applicable for whom? It is applicable for a spherical shell. Okay. Having this in mind, what we are going to do is, if I take this as the electric field and this as a distance, then from 0 till capital R, what is going to be the value? From 0 to capital R, it is 0. At capital R, what is happening? Its value is reaching a constant value. Why am I calling it as constant? Because the total charge Q is a constant and capital R is the radius of the spherical charge. That is also a constant. So it reaches a particular value. After that, what is happening? It becomes inversely proportional to R square. So the value will decrease. Is that clear? So this is what is happening. So we can say electric field is inversely proportional to R square. This value is capital Q divided by 4 pi epsilon naught capital R square, and this value is obviously a 0 at the bottom. Clear, guys? This graph you will not find it in textbook. Okay. Right. So if you are done, I'll proceed to the next part. I hope there are no doubts, right? So is it clear? Everyone. Those who are online, is every step clear?
Yes, sir.
Good. Okay. The last concept of this chapter is electric field due to a plane sheet or infinitely charged plane sheet. So write down the heading: electric field due to an infinitely charged plane sheet. Okay. So what is the first step? You obviously need a plane sheet, a rectangular sheet, in which there is charge distributed uniformly. So are you able to see this? So first draw this. So you're able to understand. So if you see a rectangle directly, it look like this. If you see the rectangle from this side, then it look like a thin line. Whereas if you see the same rectangle slightly tilted, then it will appear like this. So where some part is in XY plane and some part is in Z plane. Are you able to understand what I told? Previous. Rectangle is rectangle. Line. If you see it like this. That's what I told. Rectangle. Line. Like this. That is the type. Okay. So on top of this, there is charge present. So now is it clear for everyone? Guys, clear? Okay. So listen. You take a point P which is at a distance R from the charge distribution. So you take a point P which is at a distance R from the charge distribution. And due to the positive charge, what will be the direction of electric field? It is going to be away from it, right? And it is obviously perpendicular to the surface. Remember, this plane sheet has charge at the backside also. So if you take a paper, let's assume that the paper is charged on both the sides. Due to the charge at the backside, there will be an electric field to the left of it, accepted, right? So there are two directions of electric field. Now our job is to consider a Gaussian surface. So the best Gaussian surface that you can think symmetric with respect to the charge distribution is either a cylinder or a cuboid. So you can think of a cuboid also. In this context, we have considered a cylinder. Okay. So when you talk about the cylinder, again, how many surfaces does it have? One curved surface and two flat surfaces. So it is our job to define the area. So for that, I'll consider a small area on top of it. This is dA. One dA is on the flat surface of the right one, and the other dA is on the flat surface of the left one. Okay. So how many fluxes will come out? Flux through flat surface 1 plus flux through flat surface 2 plus flux through the curved surface should be equal to 1 by epsilon naught times the charge enclosed, accepted. So that's what Gauss law says. The sum of all the electric fluxes should be equal to 1 by epsilon naught times the charge enclosed by the Gaussian surface. Yes, it should happen, right? So curved surface flux is 0. Why? Yes, electric field and aerial vector are perpendicular to each other. So curved surface, the flux through the curved surface is 0. So what is the flux through the flat surface? E into dA plus flux through the second flat surface is also E into dA. But what should I put here, guys? I need to put a loop integral, correct? This should be equal to 1 divided by epsilon naught times. What is the charge that is collected here? What is the charge that is collected here? For that, you need to define the type of charge density. For a plane sheet, what type of charge density will you define? Sigma into, if I take the area of this curve, area of the flat surface as capital A, then what is the charge enclosed by the flat surface? Sigma into A. Think about this step. If there is any doubt, get it clarified. Pi r square. Basically pi r square. This is the Gaussian surface. Now, what does Q enclosed mean? Q enclosed means the charge enclosed within the Gaussian surface. Paper is first of all an infinite plane sheet. Okay. And secondly, whatever is present this Gaussian surface is exactly in this area only, no? The area. So sigma is the charge density. Sigma multiplied with this area is going to give you the charge that is present in this area. That is the meaning. Okay. That is equal to sigma into A, which implies 2 times the surface integral of E into dA is equal to sigma into A divided by epsilon naught. Any doubt in this step? So what is the surface integral of dA, guys? 2 into E into the surface integral of dA is equal to sigma into A divided by epsilon naught. But surface integral of A is nothing but the area of the flat surface. What did I consider the area of the flat surface to be? Capital A. So can I write it as 2 into E into A is equal to sigma into A divided by epsilon naught. A and A will get cancelled. E will be equal to sigma divided by 2 epsilon naught. So the electric field through each side. So what did I say in the beginning? The plane sheet is charged on both the sides. So due to the charge present on each side, there is an electric field of how much value getting generated? Sigma divided by 2 epsilon naught. So each side is creating a field of sigma by 2 epsilon naught. What will be the total field? Sigma by epsilon naught. So if you observe this thing, Unlike the previous two scenarios, there is something unique about this. What is it? That is okay. That is okay. In the first one, what is the expression you got? Electric field is lambda by 2 pi epsilon naught r. Second one, q by 4 pi epsilon naught r square. Here, just sigma by 2 epsilon naught means it is independent of the distance. So electric field is a quantity which is independent of whom? Independent of distance. So you remember this concept? A dipole placed in uniform electric field. So if somebody asks you how to generate this uniform electric field, what source material will you use? This is the electric field due to which source? Infinitely charged plane sheet. So if somebody asks you, tell me the source of uniform electric field, what will you say? An infinitely charged plane sheet. Because it generates an electric field which is independent of R. Okay. So the graph will look something like this. E and R, it will look like a line parallel to the x-axis. It will look like a line parallel to x-axis. Is that clear? So that is all with respect to this chapter. Cuboid is the same thing. I'll do it. Tell me, somebody has a doubt.
Sir, in the first step, you have done flux rate in first position plus the second position. Doesn't that give the total electric field?
No, E is how much? E is the electric field due to one surface. See, this side is generating E. The second side is
Yes, sir.
generating E. Okay. So the electric field due to one surface is going to be sigma by 2 epsilon naught only. No? The total electric flux is produced is only sigma by epsilon naught. That is the meaning.
Yes, sir. I'm talking about the first step that you have written.
First step na iduva.
Yes, sir.
This one sigma f phi f1 plus phi f2 adva.
Yes, sir.
In that, what we did is we took the flux q to each surface and then we started. Okay, but
Okay.
E stands for what? E stands for the electric field into each side of the plane sheet.
Yes, sir.
So this is one E due to one side of the plane sheet. This is another E due to the other side of the plane sheet. So what is the value of E that you got? That is sigma by 2 epsilon.
Yes.
So that is the electric field due to one side of the sheet.
Okay.
That is the meaning I'm trying to say. Okay, for you to understand this concept, I will take a textbook problem and solve it. See, in your textbook, they have considered cuboid. You asked me to prove it using cuboid, right? It's the same logic again. If you take cuboid, again, irrespective of the area that is going to be present there, here what will you take? A. This side you will take it as A. I mean, I'm not considering about what is the length, breadth, and height. I'm just taking it as A. Okay. Then flux through the first surface is how much? E into A. I'll directly write it. What is the flux through the second surface? E into A is equal to how much? 1 divided by epsilon naught into what is the total charge enclosed by the Gaussian surface? What is the charge present here? Sigma into A. So again, what is happening? A will get cancelled. If you try to solve it, you will get the same answer. So irrespective of whether you are going to use a cuboid or a cylinder, the answer is still going to be the same. Okay. Yeah. So I'll take one of the applications of it. There is a problem in your textbook. You should get this. It's accepted. Hmm. 1.2. Two large thin metal plates are parallel to each other. So wherever you see in physics, right, large means infinite. So two large thin metal plates are parallel and close to each other. On their inner faces, the plates have surface charge densities of opposite signs of magnitude 17 into 10 power minus 22 coulomb per meter square. What is happening? So if you try to draw a diagram, there is one sheet like this, there is an other sheet like this. Where is the charge distributed in both the scenarios? It is only inside. Read the question carefully. So one charge is present here and the other charge is present here. It is negative. And they are uniformly distributed. Where is it? Have surface densities of this thing of this value 17 into 10 power minus 22. What is the electric field in the outer region of the first plate? What is the electric field in the outer region of the first plate? Second, what is the electric field in the outer region of the second plate? And what is the electric field in between the plates? So just now we derived one thing. What is it? Electric field due to one side of a plane sheet is how much? Electric field due to one side of a plane sheet is sigma by 2 epsilon naught. So due to positive charge, isn't the electric field towards the negative charge? So positive and negative are facing each other. Similarly, due to the negative charge, what is the direction of electric field? It is towards itself. And how much is going to be the magnitude of it? Sigma by 2 epsilon naught. Is there anyone having a doubt why I didn't use minus? Why I didn't use minus? Because the arrow mark took care of it. Right? Now, third one is easy. Tell me. Third one is easy or not? So what is the value of electric field inside? This electric field and this electric field, they both are in same direction. So electric field inside is going to be sigma by 2 epsilon naught plus sigma by 2 epsilon naught. How much will it be? Sigma by epsilon naught. But sigma evolo 17 into 10 power minus 22 and epsilon naught is 8.85 into 10 power minus 12. So 8.85, if I approximately take it as 2, but 8.5 is 17. So approximately take it as 2, this will be 2 into 10 power minus 10 Newton per coulomb. So that is the amount of electric field present inside this system. Now the important question is, what will be the electric field outside the system? That is one of the reasons. And if you see the directions, right? So that is right. There is no charge outside, but there can be a question: what is going to happen due to each charge? Like if I place a test charge here, okay, if I place a test charge here, due to the negative charge, it will tend to get attracted like this, and due to the positive charge, it will tend to move this way. They tend to get cancelled. So that is another way of explaining this. So it is zero outside because the net electric fields get cancelled. Same is the case on the second side also. So if at all you wanted electric field to be present outside, what should have happened? Maybe you should have charges on the other side as well. Then things would have worked out. Okay. So the main reason why I explained this is because that sigma by 2 epsilon naught is what I wanted to register. So clear? So due to one sheet, it is sigma by 2 epsilon naught. Never forget. Due to positive charge, the positive charge is present here, right? If at all you place a test charge, due to this positive charge, I can say that it will experience an electric field in this direction. And due to the negative charge, it will experience electric field in opposite direction. So they tend to get cancelled. That is the meaning. Okay. So if you're clear, we'll do some more problems. In 5 more minutes, we can do at least 2 problems. These are all simple problems. Okay, you're done? Let's do the 19th one. So read the question. There is a point charge of 2 microcoulomb, which is placed at the center of a cubic Gaussian surface of edge length 9 centimeter. Okay. What is the net electric flux through the surface? What is the answer? So flux is equal to, what is the formula? charge enclosed divided by epsilon naught. So here one data is given to confuse you. What is it? That 9 centimeter, an unwanted data, because if it is a cube of 9 centimeter, 10 centimeter, 90 centimeter, anything, what is the net charge enclosed within it? 2 microcoulomb. So use a 2 microcoulomb and divide it with epsilon naught. Epsilon naught is 8.85 to 10 power minus 4. Simple, right? Yeah, you have those things you have to, only then the units will get cancelled. Because 8.85 to 10 power minus 12 will be in terms of SI unit. So 1.20. So there is a point charge that causes an electric flux of -1 into 10 power minus 3, sorry, 10 power 3 Newton meter square per coulomb. So what does it conclude? What do you understand with that minus sign? So whenever the flux is negative, right, it means the flux is entering the surface. When can flux enter the surface? Who has a tendency to receive electric field lines? Negative charge. So the meaning of the negative flux means the flux is entering the surface, and the Gaussian surface has a radius of 10 centimeter, accepted, centered on the charge. If the radius of the Gaussian surface were doubled, how much flux would pass through the surface? So you have a point charge. There is a point charge. So it will become 1/4, right? But the fact is nothing will change. It's nothing to do with area. Again, you need to concentrate on important. Read the first part of the question. A point charge causes an electric flux of -1 into 10 power 3 Newton meter square per coulomb to pass through a spherical Gaussian surface which is centered on the charge. So there is a Gaussian surface, and where is the charge present? At the center. So the electric flux is received, or the electric field lines are received towards the center. So whether you are going to use a Gaussian surface of 10 centimeter radius or 20 centimeter or infinite radius, as long as the total charge enclosed by the Gaussian surface is still going to be the same, nothing is going to happen. So what is the answer to this? Nothing. No change, because the total charge present inside is still the same. So what happens is, see, this is one of the important points with respect to this flux-based problems. Every time our mind starts thinking of geometrical parameters, we'll be more considerate about size. That is given only to confuse you. Most of the times we forget about Q enclosed. So whenever you are calculating flux, always concentrate on the charge enclosed. As long as it is the same within that particular surface, nothing will change. Is that clear? So that is the meaning, guys. And what is the value of the point charge? That you can find it out. They have given you the flux. So flux you will equate it to what? Yes. Correct. So -1 into evo. -1 into 10 power 3 Newton meter square per coulomb is equal to charge enclosed divided by epsilon naught. So they ask what is the value of the point charge, means magnitude is enough. And you can write, for safer side in exam, you can write that it is negative charge. Okay. Q enclosed is equal to -8.85 into 10 power minus 9, 10 power minus 12 into 10 power 3. So these many coulombs is going to be the answer. Right. I hope these problems are simple, right? So this is how you will get problems based on Gauss law. So you can try them. In the next class, we'll discuss few more problems, and then we'll go to the next chapter. But before that, as I mentioned, you'll get a worksheet. Work on the assignment. So now I can give you the complete chapter itself. Yesterday I thought I can't complete it, but it's over fortunately. So complete chapter, I'll give you an assignment. Work out on that. Okay. And then next week we'll have a test. And on Monday, can I start the second chapter? The first 15 to 20 minutes, we'll have a doubt session from the assignment. Then we'll go to this. I'll tell you next week. 35. Assignment, that depends on when I set, I'll see. 50, I'll give. So any other doubts? That's it. No? So keep revising. If there is any doubt, reach out to me on the student support. I'll see what. Guys who are online, any doubt?
No, sir.
No, sir.
No doubts, sir.
Okay, then we can wind up this.
Okay, sir. Thank you, sir.